Make sure we stay on time here. Okay, so on that guy, I have a bunch of affiliations. This work does not checkers over behind the standard disclosures. I'm not going to become rich from any of these people, but we have to do it. So I was told early in my career that people have to remember something from their talk. This is what we remember from this talk. This is the big year library. Unfortunately, the last people using it as libraries are people my age and older. Like none of the young people go to libraries, other use them as general coffee shops. So I found other users for this library. So about the time we had Kevin over to your talk deal, this is what we used the library for. Fun fact, when you see them come out, this is not the library, this is another one. This is the main real cafeteria. And that sums up it. So, yeah, so the film with Indiana Jones is kind of fun. If you, my eagle-eyed daughter, when she watched the movie, saw him opening a piece of mail, and the zip code at the bottom of the mail was a zip code for Yale, so we think Marshall College is actually here. That's the last you hear of Indiana Jones or any popular culture. I know nothing about this culture. Okay, so these are the real things to remember from this talk. And we'll talk about medical software and medical software. You'll see that in a minute. You alluded to this at the start. If your tool is used to diagnose or treat patients, it probably qualifies as a medical device and is subject to regulatory required to be able to be sold. Now that's different from things developed inside the university, used inside the university. The moment it goes on the market, that applies. The FDA actually in the US gets authority from something called the Inter-Commerce Act, Regulatory Act. It's actually commerce between states, Interstate Commerce Act. So as long as you're not selling, they don't get involved. But if you're going to survive, you have to sell. So the focus of all these things is how you approve the use of what it does. So don't think algorithms, things use cases. We'll have an example in a bit. The key question we have to remember in this business, if something goes wrong, how bad can it get? And all regulatory processes start with something called risk classification. We'll talk about this in more detail. And finally, for those of you in academia who've never experienced industry, there's a lot of paperwork because you need to be able to demonstrate that you did what you said you did. Okay, the regulatory process is a paperwork exercise. They don't run your software, they don't look at the code, they look at a bunch of papers, and they say, well, if you did what you said you did based on these papers, you're good, and if you didn't, the course will catch up with you later. Okay, that's the basic process. It's a paperwork exercise run by lawyers, not by engineers. There are other engineers involved. Okay, so here's your outline for this presentation. We'll talk about the Terac 25, which is one of the early medical software disasters that led to a lot of the stuff. I'll give you a brief overview of the medical device regulations of custom software. We'll talk about open source and dependencies and how open source plays in this space. And then this is the year 2024, I talk about AI and emerging issues. Okay, so the Terac 25 is probably the first known case of software killing people in the medical space. This is in the late 80s. These are the original sources. There's a link at the bottom. At the end of the talk, I'll have a Google Doc QR code with all the links, so don't try to take pictures or anything like that. So this person, Nancy Levinson, she used to be at the University of Washington, now she's at MIT, did a whole investigation on this, and we know a lot about this case and like what you said, the other case. So radiation therapy is a machine that looks like this. You put the patient under, you shoot radiation through to target a tumor. This goes on, because we're not involved in this, for multiple days. The key to this is that normal tissue recovers better than cancerous tissue. You give a little bit of radiation, you give a little bit of cancer, you let the normal tissue recover, you go back the next day, you give a little bit of radiation. If you're doing prostate cancer, this could be 8 weeks. If you go to this for our hospital, the parking spots right at the front are reserved for people coming in and out for radiation treatment, because they come every day for their fraction. So this is the system. This is the Terac 25. So this is now 1981, 82. This is a dual-use machine, dual form. It uses electrons for tumors near the surface and X-rays for deeper tumors. The problem with radiation therapy, to put it crudely, is you want to spare as much normal tissue as possible. Killing cancer is easy. Keeping the patient alive is hard, right? So keep that in mind. So it's a dual treatment machine, and you have this sort of gizmos in front of the beam. And if you're using X-rays, this needs to be in front of the beam to absorb some of the radiation. If you're doing electrons, you have to put this thing in front of the beam to focus with it. That's all you need to know. Those are the things. There was an earlier Therac 20 machine where there were mechanical safety mechanisms. So if the wrong filter was in front of the beam, it wouldn't let the machine kick in. They replaced this in the software. And that's what caused the accidents, is that the electromagnet was in front of the X-rays. It did not filter the radiation, but the detailed process. So this is like in the 80s. So this is how it works. You have a treatment room. The operator walks in the treatment room. They put the patient on the table. They set all the fields. They attach the accessories to the machine. They leave the treatment room. They close a giant fixed steel door, just like the dental X-rays on the back of the room more. They re-enter the patient information onto the console. And if the information matched what we said inside with what we did outside, you could go ahead and proceed. People complained that this took too long. So the company, Atomic Energy Company of Canada Limited, modified this so you could hit enter and copy the settings from inside to outside. Okay, this is how the thing works. This is what we know about it. Just one of the accidents is a mock-up of what the console would have looked like. It's a BT100 terminal, for those of you old enough to know what that is. They were doing skin cancer, so using electron radiation, shallow. The technician hit X for X-ray, then realized there was a mistake, so they pushed E really quickly after that. In the 1980s, computers could not process run that fast, so we sort of loaded the interrupt system, so it stayed on X-ray even though the screen showed that. There was a software error. The beam was still set up for X-ray mode. The system discovered there was an error and gave a wonderful message called malfunction 54. You know what malfunction 54 means? Nobody knew. There was no documentation. There was no manual. Just said malfunction 54. This created the error message. Okay, so back in the old days of DOS, abort, continue, cancel, whatever that message, the technician said, okay, you've seen this before, no worries, let's press P to proceed. The patient receives a deadly dose of radiation and the patient dies. Okay, for safety, there should be no way we're pressing P kills a patient. No operator would have thought pressing P will kill a patient. In fact, this is what happened. And so there was a whole investigation of this. They figured out all kinds of things about this, and a lot of what we will see in the medical device regulation software comes from this and similar cases. This is some of the reviews from the Levinson work. In this particular case, requirements, design documentation was written as an afterthought. They finished the device and then they documented it. If you don't do that, might as well not document it. There was no policy system in place during design development. For those of you at universities, in industry, everything happens under a policy system. There's under just how you commit code, how you push code, how you use code, who messes the design. There was no procedures in place. The user interface was confusing to the user, and error messages were cryptic. That's here explained by a wonderful message. There was inadequate software engineering. The design was overly complicated, and they only did system-level testing, which was something mission critical. And shocking to most of us in software, one of the problems is they use code from an earlier machine, but they're used to the whole testing again. What's safe here is not safe here. So that is the Therac 25. When you read the regulations, you hear that concept is. So let's talk a little bit about medical device regulation. The best summary of the medical device process has from the presentation, which I cannot track, but I found this and I had the notes, so I noticed that it's there. And he claims that there are 3 easy steps. You have to have a plan, follow the plan, and be able to demonstrate that you follow the plan. Okay? In that way. So let's see what this entails. The misconception about what dealing with the regulators involves is this column on the left. You code your software how you like. At the end, you do a validation study. You submit the results to the FDA, and you get approval. And you're happy, and that is the end of it. That is normal. Okay, this is what happens. This is normal. What actually happens, you can see it's a much bigger column on the right than on the left. You start by a quality system for your company, and you start operating underground. That is the first step of the process. You design your software and you document now. Don't think waterfall here and everything has to be designed to the MVP, but you have to have some design before you start. You do a risk analysis. What could go wrong here before you start? You account for that in your design. Very useful thing in the US, and I apologize, I don't know what the situation is here. You can meet with the FBI ahead of time and ask them questions, and they will tell you, no, we need to see this, no, this is not good enough, they're very good about that. You implement your software and document, you perform a pre-specified validation study, meaning you have figured out what you're going to do before you start, you don't just analyze at the end. You submit the entire process to the FDA. The FDA will check your quality system long before they check any of the other stuff. You get something called approval or clearance, depending on the process you follow. To you and to me and to everybody else, the two things are identical. Don't tell the FDA you got approval when you got clearance, they get open out of shape. Make sure you know what the word is. And finally, you're responsible for keeping track of your thing after it goes on the market. So it's called post-market monitoring. So everything up to here, you'll hear use the term pre-market, and this is now post-market once you start selling. Now, post-market regulations have been around for a very long time. So here's an example of almost 4,000 years old. If you go all the way back to Hammurabi, it's king of Babylon, so on the earliest law codes we have, we can read the code. The builder built a house for someone who was not constructed properly, and the house he'll fall and then kills the owner, and the builder shall be put to death. If you kill the son of the owner, the son of the builder shall be put to death. This is post-market regulation. 700 BC. And the idea is, you're selling something mission critical, you're responsible for it. It doesn't matter if you just sell. Like, this is not a use capital issue. As is, you're responsible for it. Okay. Not every piece of software you'll see in a hospital qualifies as a medical device. It's from the FDA's list. Startups used to book appointments and accounting and all that. They're fine, the FDA doesn't need to know. The apps you get on app stores, like for diet and exercise, those are fine. The FDA, at this point, pays no attention to them. They may change their mind, but for now, these are more kind of regulation. Electronic patient health records, for whatever miracle, are not regulated. The most important piece of software in any hospital is computer regulated. Storing things, transferring, storing, converting, or displaying data, they assume that this is just something to charge. Well, and finally, this is the controversial one. Certain limited clinical decision support. Nobody knows what this term means. This is a highly controversial issue. The FDA has one understanding of this. Congress has another understanding of it. Industry is suing the FDA. This is lots of fun. The idea being is that clinical decision support was, here's a guideline you're supposed to follow, and we automate it. So we don't have information with some software formula like that. The idea is that doctors are supposed to be able to do this without the computer, but this is just the process. What happens when clinical decision support is changed? Is that fine? The FDA basically says no imaging, no signal processing. The way the law is written probably doesn't imply this, so now we're in the courts and there's no computer. Okay, use cases we've played that game before, has that? Okay. So what's the object of this game? I can't talk. Anybody?
Let's discover the assassin, the tool, and the place.
Yeah. So this is the three of the four things that involve in this case. This case in this scenario. Kernel master in the ballroom, right? That's a classic one. By the way, I took these pictures already. This is how I call you the game. So, kernel master is your user. He killed somebody. That is the use case implied in this case. In the ballroom, the location with a rope, that's a tool. Middle section, the conception of reception. In an operating room, with a touchscreen computer to guide him, whatever you want to see, or plans for the procedure. Those are the elements that go into this game, the usage scenario. This drives everything. What is your risk profile? What regulatory process you're going to follow? What the FDA wants to see determined by this. Notice that we don't know what the technology is involved here, what outcomes are, just what somebody's going to do there. That is what drives it. So we see that. So, depending on the risk involved in your process, this is the US process, I'll show you the EU one in a bit. You get classified into one of three risk categories. Let's say low, moderate, and high, class 1, class 2, and class 3. Depending on the categorization, You're subject to certain things you need to do. We'll talk a little bit more about what these things are in a bit. And you're subject to different review processes. So if you're class 1, just send the FDA, thank you, I'm selling this pair of surgical class, it's a medical device. If there's any problem, let me know, and that's the end of the story. If you're class 3, you're doing clinical trials. Okay, so depending on your risk level. So software, I apologize to you with robotics, you are probably in a higher level of risk than just pure software. Software is usually class 2. You are subject to general controls, good manufacturing practices. When we say what we did it. Our address is on file, we're registered, we're not making counterfeit products, the stuff that people do. And then special controls, special to the class of software. You're doing mammography detection, special to mammography. So you're doing performance standards, 85% accuracy will be appropriate for this, it might be 73 for that, it might be 100. What kind of data the FDA wants to see as validation, as training, and what level of post-market surveillance in this sphere we can go into that. But you're subject to more than just basic general. That's the story of that. In the EU, just to sort of broaden out, the medical device regulation that came out in 2017, that was supposed to begin in 2020, that was postponed to 2021, and then 2022, and the state grandfather in the year called it out. Classifies things into 4 classes, 1, 2A, 2B, and 3, just to be complicated. Software starts out as 2A, and if it can cause death, goes to class 3, if it can cause serious deterioration, goes to 2B. Okay, the moment you bump up your class, your reforms get bump up your review. An interesting thing about the EU process that I learned in the last 2 years is that your review is not done by something like the FDA, which is a government body, it's done by something called notified bodies. Notified bodies are private companies authorized by the government ministries to review your software. Our friends in the tech industry were getting hit by the UAI Act and discovered something called notified bodies, which we need to review their AI applications if they need pilots. For those of you in the medical space, having talked to people who do regulatory work in the EU, the UAI Act is not going to be like that much different. Think about the UAI Act as imposing the medical device regulation on the rest of the EU. The only trouble is we don't know how the notified bodies will have to go through. So one for the medical stuff and one for the AI, or one body will do both. This is still a little bit of idea. If you get approval in the EU, you get the certificate. This is the CE mark. The phones probably have it, a whole bunch of the things here. This means you can sell in the EU market. The UK situation is very similar as far as I know. I don't quote me on that. The inside voting process of Brexit. And now the FDA is the last slide of the regulatory stuff. The FDA has a document that tells you what they would like to see in a submission. And you can kind of see the components. I don't think I want to read them, but the description of your software, the risk level, your design documents, your development configuration management maintenance plans, your testing, your version history, and anything that's still hanging, the software doesn't work in these edge cases. So that is the documents they would like to see. The first thing they ask you to do is whether you need normal documentation or enhanced documentation, depending on the risk of the software. And so all of those documents become more comfortable with your recovery. That's basically the list. We'll come back to this. Any questions so far? Yes.
The last slide I mentioned in this. How is it different from class 1?
Just details? So if you, first of all, this is for the software component. If you have a hardware device, you may have different gradations for the hardware and for the overall thing as opposed to just the software. But the first part you're going to hear is this low risk or high risk? So if you're subject to enhanced level documentation, they're going to want detailed designs as opposed to high level modules. They're going to want to see unit testing results as opposed to just overall testing. So it's stuff like that. I'll take one more question.
Yeah. So only to comment on that, basically for C, there is a standard for software lifecycle, and we have another classification, which is ABC or ABC, and depending on that classification, it decides what kind of documentation.
Yeah, I know, and implicit in all this is that the FDA, you can tell if they will follow the ICC 6304, and then you're happy, other than for the fact that 6304 is 15 years old and how to verify and the best way trying to fix it. We'll see. Let me continue and then get back. Okay, so since this is open source, also we talk about open source and software dependencies. So almost every piece of software we will write, we use code that we will not write ourselves. Okay, have you guys ever written anything that you wrote every large piece of line of code, starting from the operating system up? Yeah, I know. I was looking at it, thinking maybe Peter will be doing the other robotics. They have had experience. There's one example that we've seen in this talk that we've done is called the Parent 25. We wrote the operating system. It didn't work out well. And so writing all of your code is not necessarily bad. We don't have the expertise to write that. The issue often when we're using external code, some of control or provenance, we know where the code came from. We have design documents, we have verification of right code, all of those things. You'll see these two terms thrown around. OTS is left later, off-the-shelf software. You need some library from somewhere. Commercial open source. SOUP is the IC234 term. Software of unknown provenance, software we don't know where it came from. And that's not stupid. Software we don't have documentation for. Fun story in GE wrote part of ITK under a contract from the NIH, right? When ITK was coming out in the 2000s. When GE used ITK in the medical devices, they had to label it as software of unknown provenance because it didn't have a quality system. Even though they wrote the ITK part, but they were using the software of unknown provenance. It's kind of a fun case. The left hand did not know what the right hand was doing. And my advice generally is try to minimize your dependency on external libraries. Obviously, you use them, but don't just use everything. The nuclear weapon of software development is P or NPM. Like, hit install and you get half the internet, and now you good luck. And you keep trying with that. But you obviously have to use some. It's the one generative AI picture installed. Definition of the SOUP. Software for which we do not have audio. Okay? This includes, just as a reminder though, the fact that you're using somebody else's code in your medical product doesn't make them liable unless you have a commercial agreement with them and you're liable. You are the manufacturer, you're responsible for everything. Okay. In your submissions, you need to identify the external components. You want to use well-known, widely used, well-tested libraries. If the FDA has seen the same thing 100 times, they want to specialize. If you're using Xenophon's latest linear algebra library that was used by exactly one person, that's really not a good idea. You need to justify why used, and you describe some testing process for your children in a bit. For open source code, there's nothing really different about open source versus closed source at this space, other than for the larger operating system typically. You want to select libraries with a large user base. You want to look for testing and documentation. A lot of open source is high quality, they're not commercial code, because lots of people are involved. With some parts of open source libraries of high quality, there are edges of open source libraries, a different story. You need to freeze the version, you're not really syncing to the GitHub repo. And then for those of you asking, this is not everybody in this room, they're licensing open source like GPL licenses, where if you use GPL, everything becomes GPL. With PSP licensing is what most people use. I need to acknowledge industry in terms of what GPL like they're playing, unless it's for server-side products, which is this is a typical example of a documentation when you do the library and the regular submission. This comes from some friends, common called Analytics, and they will actually, if you ask them nicely, they'll give you a full 510 application to the website. The name is going to be advanced, no matter what. But this is for Monai, for repository. Recently, this is the version, they froze it to that date. This is why they're using it. Specifications, 8 gigs of RAM. How does it assure end use by the end user? The user doesn't touch Monai, it gets touched by other things, and it explains why they're using it and how they test it. So that's typical implementation that we need to provide. Monai is well known. We don't have to tell them. The less more it is, the more they will. This is the last slide of the software engineering. Just a little bit of advice. One of the things for those of us who've been in this business a long time is that our code lives for a long time. Right? This is code that we don't have to write. So when you use external libraries, use them with care. So if this is your software, this is your code, module 1, 2, 3, 4. These are your libraries that you're going to use, 1, 2, 3 here. The question is, do you call the each library directly from here, or do you call it to some mediating mechanism? When I show this to students, I say, well, Are you dating or are you getting married? If you think that this library is going to be in your software forever, right? You're doing Python and this is NumPy. You're not going to see out of NumPy. You're stuck forever. Feel free to pull it from everywhere. But then NumPy is going to be with you for the duration of the life of your software. If this is some database access library that you may change 5 years from now because you may use a different database, my advice is don't call it directly from your code. Have a little bit of a funnel and then call it through that. So if you do decide that you only need to change this piece. When we were developing our own version of the software, for us, this was VTK and this was ITK. We use ITK a little bit peripherally, so we always converted data structures, called it back, converted, whereas VTK data structures were strewn all over our code. The code is written. So that is that. Any questions so far? I have one more section. Anything else to start with? Okay, and then given the year we're living, we'll talk about machine learning and AI. But this advanced a little bit. I'm going to here. Just give you a little bit of an overview of where we are in this phase. So AI has been around forever, and the hype has been around for a lot longer. This is from the New York Times. This is 1958, okay? And just to read the highlights. This is advancing by itself. Okay. We'll try to, this is a computer? Let's see if I can just pause it here. Okay, let's keep to that. The Navy revealed the embryo of an electronic computer today that expects to be able to walk, talk, see, write, and produce some of the conscious existence. No hype. No very ambition. 1958. The embryo, the Weather Bureau is getting reflection. $2 million 704 computer learned to differentiate between left and right after 50 attempts. They were able to do left and right, and they were able to walk, talk, see, reproduce itself to conscious existence. Okay, no jumps from what we can do to what we promise to do. The survey said it would use this principle to be the first of its perceptron thinking machines. Perceptrons like the one-cell neural network, okay? It will be expected to read and write, so conscious existence stuff has just dropped out by the third paragraph. It's expected to be finished in about a year at a cost of $100,000. As I've mentioned, that about 60 years later, we're almost there for some of these things, not conscious of existence and reproduce itself. So AI has been overhyped for a very long time, and that's true too. There is times when okay, so in old-fashioned terms, those of us convincing a computer to do something. Let me see if I can just push this back instead. Okay, there are two ways to convince a computer to do something. This is just saying, right? Let's call it the explicit way. We describe all the rules in detail. The human rights what they call. This is what we call software engineering tradition. It's explicit. We give it the rules, but we have an implicit way. We don't have rules. We have input-output examples, and we use some kind of machine learning to learn them. One's explicit, old-fashioned software engineering. The other is implicit. We have examples and put out the code from there. When the thing is explicit and we know the rules, it's relatively easy to think about how we test it, but we know what the thing is doing, we can break it down into pieces. When it's implicit, now we have a problem because we don't understand. There's no way to break down the output into steps. So just keep that in mind. That drives a lot of what we do. By the way, those things apply to all kinds of other areas of life. If you get into things, we're going to pass through here. Go back 2,500 years, you have the ethics books, rules for life, do this, do that. That's the explicit, that's the software engineering. And then the alternative is lives of heroes and great people. Learn from examples, we don't know the rules, but if we read their lives, we can pick up examples. So you're going to see that phenomenon in all kinds of other elements. Okay, when you think about AI, I want an AI that does this, and I want an AI that does that, I want an AI that does that. If you live in a hospital, everybody wants an AI that does something. So this is my example. When people think about AI solutions, they need to realize that AI comes as part of the software package. There's no freestanding AI. My visualization of this for my students is think about the software as the car and the AI maybe as the engine. The AI is a piece of the car. Please remember, Nothing else. You just like parks and engines. If you look out the window and go on the street, you will not see naked engines driving around. You only see cars. There's no naked AI driving around. Part of a larger thing. How the engine fits in the car, of course, is critical, but other things, brakes, seats, comfort, mirrors, affect the user as much as the engine. Okay? When we bought our van a million years ago, my daughter picked the place on the color. We tried identical maps. I didn't try to give her that level of choice. I didn't give her that level of choice. But a lot of the problems with AI will not be solved with the not be solved in the system. People say, well, how do we fix AI? Not hallucinate. We can't. It's going to be the supporting infrastructure around it that prevents it from getting involved. So don't think that all problems in AI are going to be solved in AI. Not all problems in the engine are the engine. We have brakes. They're not part of the engine that control it. So keep that. That's sort of the minutes. Sorry? I mean, a little bit faster. Not what the tool does, but what it is used for. If you're using it to generate a movie sequence, you can fail 99% of the time, that's fine. If you're using an AI tool to pose image for a trial, that can fail 5%, that's fine. Same tool being used to diagnose patients with disease of popular. Same exact piece of software. Nothing has changed about the tool. Changing use case. Okay, so there's a bunch of new documents just for out of time. The FDA puts together machine learning practice document. You can find that. There's another one on internal change control plans. This is to allow you to update models rather than go through regulatory review. This is early days. And there's a third one that just came out a couple of weeks ago on transparency. These are issues of explainability. The UK situation is a long page that describes all of their things. And finally, there's a technical report came out of Amy about the risk management for AI. It's already out of date in the old, but we can go through this. I'm not going to cover this. But these are the three major things that they think are different between machine learning, traditional regular devices. You can learn, you can be autonomous. Okay, to conclude. Okay. Information distribution has basically gone like this in history. 50% in 1450s, internet 1990s, the iPhone, internet in your pocket, generative AI. That's a picture of the Gutenberg Bible at the library from the left. It's the first time that technologies demonstrate the ability to work to replace people who write for a living. Now they're complaining. So there was not a ton of concern for the loss of jobs for people who used to do computers. Computers people work at accounting offices doing now. But now we're replacing journalists, so there's an explosion of interest in this topic. And so everything we do is an explosion. And we conflate fluency and intelligence. Somebody who speaks well, they think is smart. And Wesley, somebody who's smart must speak well. I can give you 2 examples of these breaks. The new graduate student who comes to the US from a foreign country is really bad, but I might do 180. People treat them like a 5-year-old because they're not fluent, therefore they must not be intelligent. ChatGPT is really fluent, so it must be intelligent. Keep that in mind. That is it. We have a bunch of challenges with generative AI, control of data. There are no use cases specified as the device was developed, so what are we doing with it? Validation is almost impossible because everything's an edge case. It's a huge potential. How do we integrate this with the rest of the system is going to be fun. How we integrate with the user is going to be fun. Explainability. How we integrate the user in the system. If we're relying on the user to catch errors, then the user is only part of the system. So think about that as another interface. And again, not what it does, but what it does. Not, I'm going to use generative AI and medicine. We use it here and we won't use it there. That is okay. So I'm going to just flash this slide of research. Again, mentioned there's a Coursera class that we reported on this. This is basically free. You can take it. As of 2 weeks ago, we can 2,000 students registered. Since we're in the global health business, about 10% of the students are in Africa, about 30% of the students are in Africa. 13 hours of videos takes about 37 hours. There's a textbook that I wrote at the same time as the Coursera class. I had a copy there. I'm sure this is my day teaching. I keep for my students, I make my students present this and use of software accident stories. If you're curious, you can go see different things of software field. For those of you in industry who started with a certificate program, this is more the hybrid education, pre-recorded lectures, live Zoom sessions. This went on for 16 weeks, we're just finishing this week. 16 people this year from 6 countries, or maybe a little bit bigger, the names at the bottom. And then the last thing is that there's a YouTube channel on the Yale American Medicine Data Science, a bunch of talks on AI and software. And for the needs of the certificate, I interviewed a whole bunch of people with clips of this in the slides. You can watch the whole videos online. And to conclude, that's the QR code that takes you to Google Doc that has all the links that were in the top. So you don't have to worry about taking pictures of the slide and hold them time.